This is the seventh topic in the probability and stochastic processes course, in which we are going to talk about random walk. Random walk has a lot of applications in computer science and in stochastic processes. Random walk are usually used to model situations in which an object moves in a sequence of steps in randomly chosen direction. Random walk can proceed in a space, in one-dimensional space, two-dimensional space, or three-dimensional space, but each time it moves, then the direction of the movement will be determined randomly. This has a lot of applications in gambling, and also it is being used in Google search computation of the page rank. Now, in this lecture, we are going to focus ourselves on one-dimensional random walk. That means that the object moves in one-dimensional space. And for the time being, we are going to focus also on unbiased random walk. That means that the object only moves to the left or to the right on the one-dimensional space, and both movement to the left and to the right happens with probability 1/2. We assume for the time being that the object cannot stay in one position in one time step. That means that it is either moving to the left or to the right. It cannot stay in a particular position in every time steps. But this is of course quite restrictive in the sense that we can imagine a random walk in which staying in one position is allowed. Now, each time we are defining a random walk, we also define some boundary conditions on this random walk. These boundary conditions are also called absorbing barriers, namely the positions in the space in which the random walk ends, or halts, or halts after some time. Now let's look at this figure. In this figure we have a one-dimensional random walk, and there are w plus 1 positions, namely starting from 0, 1, 2, 3, and so forth until w. Now positions 0 and w are the absorbing barriers. That means that when the object hits either of these two barriers, then the random walk is considered stopped. It halts. Now, in the beginning, initially, the object is placed at some position, some arbitrary position on this line. So, for example, assume that we position the object originally at n. Now then, the question or the problem that we are facing in unbiased random walk, such as this, is that starting from n, namely the object is positioned at n, what are the probabilities of absorbing or ending, namely hitting the absorbing barriers at 0 or at w, or is there any probability also of never ending, namely keep moving on in this one-dimensional space? Now these are the problems that we are going to solve. These are the problems that we are going to look into at this course. Now, to gain an intuitive understanding, let's take a look at an example. This is a very simple example in which we have an unbiased random walk with only 4 positions, namely position 0, 1, 2, and 3. Pay attention that position 0 is an absorbing state, and 3 also, similarly with 3. So there are only 4 positions. Now originally, assume that the object is placed. Now, initially we place it on position 1. Now then, we are going to see the evolution of the position of this object and how it moves during the random walk. Because this is an unbiased random walk, then movement to the left and to the right happens with the same probability, namely 1/2. So if at time 0, for example, the object is in position 1, then at time 1, it either moves to the left, namely to position 0, or move to the right, namely to position 2, with the same probability 1/2. But if it decides to move to the left, then it hits the absorbing barriers. This means that the random walk is just finished. Yeah. So we basically stop the random walk, and that's the final configuration. But if it decides to move to the right, then it moves to position number 2, and in this case, then it can proceed. It can proceed in either two directions, namely to the left and to the right again. If it moves to the left, then it returns to position 1. But if it moves to the right, then it hits another absorbing barrier, namely at 3, and so on. So you can imagine, we can basically lay it out. We can basically draw all of the possible traces or path that can be traversed by this object. Yeah, the complete path. Of course, the complete path will be unending, but then we can see some patterns. Yeah. For example, if the question is the probability of absorbing to 0, then we can see that this happens with the summation of these probabilities. Yeah. So the object basically hits it first with probability 1/2, namely at the first time instance, and then hits it again with probability 1/8, namely taking this path. So 1 to 2, 2 to 1, and then 1 to 0. Yeah. So there are three transitions, the three walk, basically the three steps that are being taken. In other cases, there are 5. Yeah, for example, taking this path, namely from this one to this one to this one to this one and to this one. There are 5 steps that must be taken, and it happens with probability 1/32. Why? Because there are 5, and each time happens with probability 1/2, or 1/2 to the power of 5 is equal to 1/32. Now, and we can see the pattern based on this. Yeah. And we can sum them all up, and the sum will result in a geometric sum, an infinite geometric sum actually. 1/2 plus 1/8 plus 1/32, and so on and so forth. And this is equal to, take out the 1/2, yeah, to the front, multiplied by 1 plus 1/4 plus 1/16, and so forth. And this part is a geometric sum, infinite geometric sum, and you know how to deal with that, which is equal to 1 divided by 1 minus a quarter, and this is multiplied by 1/2, resulting in 2/3. So the probability of absorbing to 0 is therefore 2/3. What about the probability of absorbing to 3? Similar reasoning can be taken. So right now we are observing the absorption to the absorbing to the right absorbing barriers, namely at position 3. And this happens with probability 1/4, namely taking 1 to 2 and 2 to 3, or yeah, with happens with probability 1/16, namely 1 to 2, 2 to 1, 2 to 1 to 2 again, and then 2 to 3, and so forth. And we can see also similar patterns arising. So we just sum them all up. A quarter plus 1/16 plus 1/64 and so on and so forth. This is equal to a quarter multiplied by 1 plus 1/4 plus 1/16 and so forth. And this is again a geometric sum, and 1/4 multiplied by 1 divided by 1 minus 1/4, which is equal to 1/3. So if you look at this, then for this simple example, the probability of absorbing to 0 is equal to 2/3, while the probability of absorbing to 3 is equal to 1/3. So there is nothing left because the whole probability sum up to 1. Therefore, we conclude that the probability of never absorbing, namely taking an infinite path without ever hitting the absorbing barriers, is equal to 0. Yeah? This can never happen. So this is basically our conclusion. So we have managed best right now to answer these 3 questions. Now let's look for the general case. We are not going to solve something particular, but we want to solve the general case. Go back again to this figure. We see that we have here a random walk, and there are W plus 1 position, namely from 0, 1, 2, 3, and so forth until W, and 0 and W here are the absorbing barriers. Originally, the object is positioned at N. Yeah? So it is put in location at position N, and it can move to the left and to the right with the same probability, namely 1/2. So this is also an unbiased random walk. Yeah. Now what do we want to know? What we want to know is the probability of absorbing at either 0 or W in this case. But this is not concrete anymore because W can be anything, N can be anything, and so on. So how do we solve this general case? Well, we are going to solve this by taking an intuitive understanding of the problem. Yeah, we want to model this first. One way to model this is actually, an elegant way to model this is by using a recurrence, because we can actually see a recurring behavior in this random walk. Let Rn be the probability of absorbing to W. Pay attention to W. If you want to 0, this is a different matter altogether. Starting at N. Now, Rn is governed by a homogeneous linear recurrence given here. Let's focus ourselves first on this recurrence, namely Rn is equal to 1/2 Rn minus 1 plus 1/2 Rn plus 1. So this is actually natural. Namely, if the object is in position at position N right now, then it can move either to the left, namely to position N minus 1, or to the right at position N plus 1, and this happens with the same probability, namely 1/2. Okay, so this is the main recurrence. But aside from this, we have of course boundary conditions. What are the boundary conditions? Pay attention to this one. R0 is equal to 0 because what? Because when we put the object at position 0, then absorbing to W happens with probability 0. Yeah? Whenever the object hits 0, then a probability of absorbing to W then becomes 0. What about RW? RW means that we put W, so we hit W, or we are originally in W. If you are originally in W, at position W, then right away you hit the point. So that means that the probability of absorbing to W is equal to 1. So these are the boundary conditions. Now, one more other thing that we notice in this homogeneous linear recurrence is that this main recurrence does not look natural, because on the right hand side we have something that is less and more, yeah, than on the left hand side. And this is not usually how we see recurrence. But we, of course, we can uh, rearrange this, yeah. So we can rearrange this to become 1/2 Rn plus 1, yeah, is equal to Rn minus 1/2 Rn minus 1. So this is right now becomes more natural to you. Therefore, Rn plus 1 is equal to 2Rn minus Rn minus 1. So this is right now our recurrence. So then, how do we solve this? Well, the only thing that is left for us to do is actually to solve this recurrence. Yeah. So let's solve this recurrence. We take out the main recurrence, and you're going to solve this. Every time, because this is a homogeneous linear recurrence, every time you find a homogeneous linear recurrence, then we assume that the solution is given by Rn is equal to x to the power of n. Yeah. So if this is our assumption, then of course the main recurrence right now, Rn plus 1 is equal to 2Rn minus Rn minus 1. So if Rn is equal to x to the power of n, then this is x to the power of n plus 1 is equal to 2 times x to the power of n minus x to the power of n minus 1. Yeah? And we can divide the left hand side and the right hand side by the smallest power, namely x to the power of n minus 1. So this result in x to the power of 2 is equal to 2x minus 1. Yeah? And this is equal to x square minus 2x minus plus 1, yeah, is equal to 0. And this is what we call usually as the characteristic equation. Yeah, remember this. And the root of this characteristic equation is equal to x equal to 1 twice. So therefore the root x1 is equal to 1 and x2 is equal to 1. Because we have these two roots, then the solution of this recurrence is given by the linear combination of these two. Yeah. So the solution is given by Rn is equal to S multiplied by x to the power of n. X of course can be 1, yes, plus t multiplied by x2 to the power of n multiplied by n, because we have two similar roots, yeah, where s and t are real numbers. And this is equal to s multiplied by 1 to the power of n plus t multiplied by 1 to the power of n plus, multiplied by n. Yeah? And this is equal to, well, 1 to the power of n is just 1, s plus tn. This is where s and t are real numbers. Now, what we don't know are s and t. These are basically the coefficient of the linear combination, and we have to solve this. We have to find this. How do we find this? Well, we can use the boundary conditions. The fact that R0 is equal to 0 and then RW is equal to 1. Yeah. So therefore R0 is equal to S plus T multiplied by 0 and this is equal to 0. Therefore, our conclusion is S is equal to 0. As simple as that. On the other side, we have RW, which is equal to S plus T multiplied by 1. And this is equal to 1. But because S is equal to 0, then S this is W, so I'm sorry, T multiplied by W. Because S is equal to 0, then we can conclude that T multiplied by W is equal to 1. Therefore, T is equal to 1 divided by W. Yeah? So therefore, the final solution, namely once we find out S and T is equal to Rn is equal to N divided by, so because S is equal to 0, yeah, T is equal to 1 divided by W, so N divided by W. Remember that this is the probability of absorbing to W starting from N. Yeah, so this is our conclusion. Now reaching or W happens with probability N divided by W. What if we are interested in reaching 0, the probability of reaching 0? In this case, we have to modify the boundary condition of this homogeneous linear recurrence. In this case, then R0 will become 1, because that means that when we are at position 0, then we already hit our goal, and it happens with probability 1. And in contrast, in this case, RW will become 0. And you can try it yourself. You can try to solve this. And if you try to solve this, you will find out that the probability of reaching 0 starting at N is equal to W minus N divided by W. Therefore, the probability of never absorbing is equal to 1 minus N divided by W, namely the probability of reaching W starting at 0, minus W minus N divided by W, namely the probability of reaching 0 starting from N, and the result is 0. That means that the probability of never absorbing is, again, no matter how large W is, yeah, still equal to 0. What if the right barrier does not exist? What does it mean? It means that in this case, W can extend indefinitely to the right, go indefinitely without ends to the right. So the only absorbing barrier that we have right now is 0. What happened in this case? Yeah, what will be the probability of eventually reaching 0? What if the barrier does not exist? We can wander to the right indefinitely. Yeah. Then in this case, the probability of reaching 0 starting at any position N that you like, yeah, is still given by this one, namely WD minus N divided by W. But W right now is something that approaches infinity, because this can go indefinitely to the right. So we take the limit of W is approaching infinity. W minus N divided by W is equal to 1. What does it mean? So if there is no absorbing barrier on the right, the probability of reaching 0 in this case is equal to 1. Absorbing to 0 is still a certainty. So there is no way for us to wander indefinitely to the right without absorbing. This is the end of our topic of random walk.